Alright, this will be my best shot at inverse trig derivatives. This section, or this content, is actually found in section 3.6, but 3.6 was difficult enough. It was implicit differentiation, so didn't really want to add all this on top of that. So we're taking one day just to focus on inverse trig derivatives by itself. Alright. So first thing, if you look at the graph of y equals sine x, I think we're all pretty familiar with what the graph looks like. It would go, up like this. It's at pi, and it comes down, and then of course it does the same thing, the other direction. And these spots here, pi halves and negative pi halves. Okay, goes up to a high point of 1. Goes down to a low point of -1. Now, if you look at this function and you say, okay, I want the inverse of that, you wouldn't be able to do it because that function right now is not 1-to-1. So we have to figure out, right now it's not 1-to-1 because, we keep repeating the y values and it would not pass the horizontal line test. So it's not 1-to-1 right now, but if we restrict the domain, then we can make it 1-to-1. And so they've decided to define the inverse sine function to be from right here, negative pi halves, to right here. And you can see that now if we were to just restrict that part, this part right here, the part that I'm saying is purple, if it allows me to, is going to be 1-to-1, this whole area here. And so we take this area here, this is 1-to-1, and we're going to go ahead and switch the x and the y. And if we do that, we're going to get a different looking graph. So I'm going to take, remember how the domain and the range switch when they're inverse functions. So pi halves 1 was that point there. So now it's going to be 1 pi halves. So 1 pi halves. So that's going to be that dot right there. And then this spot was 0, 0. Well, it still is, because we switched the coordinates, it's still 0, 0. This spot right here is negative pi halves, comma, -1. So we switch that, so it's -1, negative pi halves, so it's down here. So when we switch a bunch of the other points, we get a rough sketch. It looks something like this, very roughly. It lets me. Okay. And you can actually graph that on your calculator. Here's the function we're looking at. We're saying this is x equals sine y. And all we did was just switch the x and the y. We just switched these guys, the x and the y. And then if I try to get the y by itself, then this function is y equals inverse sine of x. And we use that little -1 there to show that it's actually a inverse function, inverse trig function in this case. Okay? So you can graph this on your calculator too. You could go y equals, find the button that's inverse sine of x, and you'll get that little sketch of the graph. All right. Same is true about cosine. So if we look at that, we look at cosine x, look at some key spots here. So let's say pi and 2 pi here. So this graph looks, something like this. Comes down, goes down to a low point, and then goes up. And we would say that this graph is not 1-to-1 either, but the way that they've decided to restrict the domain here to make it 1-to-1 is they go from 0 to pi. So this part here, this is the part that they've restricted. So 0 to pi. Would you agree that this part at least is 1-to-1? So that's how it's defined. So if we switch the x, this is y equals cosine x, sorry, y equals cosine x. So if we switch the domain and range, then we would have the inverse function. So the x equals cosine y. And if we isolate the y, then we're going to have the graph of inverse cosine x. Y equals inverse cosine of x. Now, as far as the sketch, we're going to just keep switching the points. So let's say this point is 0, 1. Well, now it's going to become 1, 0. So it's going to be right here at 1, 0. And then let's say we take this point, that point there is what, like pi halves 0. So then it's going to be 0 pi halves. And then, and this is pi, it will be. And then what else? Right here, we could say this is pi negative 1. So now it's going to be negative 1. Now it's going to be negative 1. If it lets me, negative 1 pi. So that would be a dot right there. And this roughly looks like this. And if we graph that on the calculator, y equals inverse cosine of x, that's what the graph would look like. Okay? So that's just kind of what is an inverse trig function in general. We haven't even gotten to the derivatives yet. All right. The next slide, you actually need to pause and take the time to copy these down. Take you a little while. But you actually need to memorize this list. And it's really not too bad. The ones that I would say are really key are definitely the left ones in black. But I do see some of the other ones, sometimes the secant, sometimes I'll see some other inverse trig derivatives on the AP practice tests, from the past. But more than likely, the ones on the left are the really, really big ones to memorize. So it's not too bad. Like every one of these, sine of u, if I take the derivative, it's just going to be 1 over the square root of 1 minus whatever's in that spot. Whatever's in this spot right here, it just goes right here and you square it. And then the chain rule always applies, so you always have to multiply it by whatever the derivative of the inner function is. So whatever the derivative of that is, you just multiply by that. So this little du dx is just showing you that the chain rule always applies. Okay. All right, and we'll look at an example how we apply these definitions, but you'll definitely need to pause so you can get all those down. All right, let's go ahead and try an example. All right, so example 1, you'll see how straightforward this is. So we go ahead and we want to find the derivative here. So we're going to say y prime equals, and all you have to do is you have to go 1 over, the form says this, it's 1 over square root 1 minus, sorry, we'll take the difficulties. 1 minus, and then whatever.
Good afternoon, Mount Point. Anyone still on campus attending our TSEA campus council meeting? We're having it at 3:45 in the faculty cafeteria. Once again, anybody interested in attending our campus council meeting for TSEA, it's in the faculty cafeteria at 3:45. Thank you. Have a great day.
All right, thank you. So we take whatever's in this spot, so that's x squared, and we square it. According to the formula, we put it in that spot, and then we square it, so whatever's there. Then we always have to multiply by whatever the derivative of this function is. And the derivative of that function is 2x, so that's what we write. And so we have that. And if you wanted to simplify it a little bit more, then you could say y prime equals 2x, and then on the bottom it would be square root 1 minus x to the 4th. Okay, so there's that one. All right. The next one is y equals inverse cosine of 1 over x cubed. So just find the derivative of that. I would say it would help to maybe think of, this quantity here. Think of this as x to the negative 3, of course. Sorry, that's a little messy. So think of that as x to the negative 3 because you could pop it up to the top. So now we're going to go ahead and just apply what the derivative says. So y prime equals 1 over, and it's negative, this one's negative. Other than that, it's exactly the same as the inverse sign. 1 minus, and then whatever's in that spot, we're supposed to square it. So x to the negative 3, and then we square it. And then we still have to multiply by the derivative of the inside. So the derivative of the inside is using the power rule. So we bring the negative 3 out in front, we write, then we write x, and then we reduce it by 1, so that becomes negative 4. Hopefully it'll let me, okay, so that'll be negative 4. And then if you want to clean it up a little bit, you could do this. You could say y prime equals, let's see. got a couple negative signs, so you can just make it a positive. So 3, and I think I'm low on my stylus battery, which is bad. So I got 3, and then that's x to the negative 4, so I'm going to put that to the bottom, and then I'm going to say this would be 1 minus x to the negative 6. Okay, so that would be my final answer. All right. This one is arctangent, which is really, it's the exact same thing as inverse tangent, so I wanted to throw that at you there. So that's the same thing as inverse tangent x. Okay, arctangent, depends on the bug. But you do have to notice that this is two different functions. You've got one function that's 1 plus x squared, and you've got another function that's inverse tangent x. So we're going to have to use the product rule. So we're going to apply the product rule. And so we're going to say h prime of x, and we're going to take the derivative of the first. So the derivative of the first is 2x, and then times the second. So I'll just write arctangent x plus, and then derivative of the second. So that's 1 over 1 plus x squared, and then times the first, 1 plus x squared. And then this simplifies a little bit, so it's going to be h prime of x equals, it would be 2x arc, it's not going to let me write that, arc tangent x, and then plus, and then those would cancel out, so plus 1. So that would be our final there. Okay? So that's really how it works with all these. Just use, whatever they say the derivative is, you just apply it. All right, the next thing I want to show you is how in the world they come up with these formulas for the derivatives. So I just want to end with this. So we start off, let's say we start off with y equals sine x, and we want to, see where the inverse sine comes from. Well, first of all, let's go ahead and switch, the x and the y. So x equals sine y, and you know that this is exactly the same thing as y equals inverse sine of x. It's just that this one over on the left doesn't have the y isolated, but it's exactly the same thing. So what I'm going to do is I'm going to say, hey, well then let's try to take the derivative of this and see what we get. So let's take the derivative of both sides, so d dx of x and d dx of sine y. Well, if we take the derivative with respect to x on the left-hand side, then it would just be 1. That's kind of nice. And the derivative of the right-hand side is going to rely on implicit differentiation, so it's going to be cosine y, and then you have to multiply by the derivative of that, which would be y prime. So we're going to isolate the y prime. So we have y prime equals 1 over cosine y. Now that doesn't look like the derivative, from that chart. But what you can do is remember your trig, and you can come over here and say, okay, I remember my Pythagorean identities. Sine squared y plus cosine squared y equals 1. And I'm going to try to isolate the cosine. So I've got cosine squared y equals 1 minus sine squared y. And then I can take the square root of both sides. So cosine y would be plus or minus square root 1 minus, remember, 1 minus sine squared y. Sorry, that's a little messy there. You can overlap. So what I want to do is I want to then replace cosine y with, actually just the positive there. So I'm going to say y prime equals, let's see, 1 over square root 1 minus sine squared y. And then you look at that and you say, wow, that still doesn't look like the same thing from any of those charts. But if you look at this, you notice that sine y is actually equal to x. And so we replace that. So finally, last step, we could say that y prime equals, and we replace the sine with sine y with an x. So then we would get the form that we're that we're expecting. So that would be 1 over square root 1 minus x squared. And that's why that's the derivative of inverse sine of x. Okay, so it kind of just gives you an idea of where that comes from. Tomorrow we'll work these out in class, and we should be good. All right.